And so that left area method to find precise calculation on a standard normal distribution can even be applied in a much further situation. So let's now get ourselves into a different example over here where we're in a different class of problem. So let's say, once again, we're being on a standard normal distribution, that famous N01 right here. And highly recommended again. Go ahead and draw for yourself an empty bell curve, getting ready for action. And so the axis here is having all that values of my random variable z. That nice center in the middle is where the mean value is, and standard deviation equals 1 being noted here somewhere. Okay, and so now let's look at question in part A. Let's find the probability where our z-score is anywhere in the interval from, how about, negative 1.5 to anywhere less than or equal to 2.05. And once again, as soon as we have the question written down, the only first thing we strictly need to do, go ahead and make the shading, make a sketch of the shaded area describing this question right here. So we now have a definite interval. So the low end of the interval here is somewhere on the left hand side, or just whatever comes out from the reading here, negative 1.5. So negative 1.5 here, and the other end of the interval is a 2.05, and how far away, it's just what really needs to make sense here is a slightly larger than negative 1.5 away from 0. But so now the shading we're creating is here. All that shading. Okay. And so here, now I'm going to point out a planning right here. So remind yourself or make a recall about the left area methods. Before I introduced the method, I was making a claim that every z-score from where it stands on the bell curve has an area cumulatively shaded to the left-hand side. And so in this problem, we're actually having two different z-scores that defines our interval. So either one of the two z-scores here, the low end of the interval or the high end of the interval, they each one of them has an area shaded to the left-hand side. And so here's another picture that I'm going to make right here. So as a planning, so here's how it works. Let me bring everybody into a brand new clean picture of my problem right here. But negative 1.5 z-score is here on an empty bell curve, and 2.05 is here. So as I just said earlier, every z-score has an area shaded cumulatively to the left-hand side. So let's start out with this upper z-score right here. So from where it stands, here's the accumulated area to the left-hand side where we can calculate using technology. So all that here, and of course I'm accumulating even outside of that negative 1.5 right here. So all that area accumulated to the left-hand side. This area we can find an answer, and let's for now name that. So this is the area, okay, left of 2.05. So that area here, let's look at what calculation is coming out for us. That area there to the left of 2.05. So now I'm going to run my LSND program. 2.05. It gives me an area being 0.9798178. So this is the area completely shaded to the left-hand side of 2.05. And I repeat that. But you can now, looking at the picture, and tell that this is not the answer we're looking for. The answer we are looking for is in between here only. It's this area between these two. And you can see that now I'm making a double shading right here. So what's the next step right here? And you can see, again, let's now look at our low end of the interval. The low end of the interval has an area cumulatively shaded to the left-hand side too. So instead of making a shading, it's already had a shade, but let me catch your attention by doing this. How about I'm going to erase that area, but only starting from negative 1.5, I'm going to erase it out. And there's a reason why I'm doing the erasing work right here. So we're erasing out that area. We're removing out, we're taking out the area to the left of negative 1.5. Okay, and so how big is that area to the left of negative 1.5 that I took out? So the empty area now that I just took out, you saw that right in front of you, that area left of negative 1.5, how big is that area? Once again, calculation on my LS&D program, or you can use your online resource to find out, but negative 1.5 gives me that area left being point, and on screen it's showing 0.0668072. So this is the empty area, or the area I just now removed out. And so think about it. The plan now is, and before I get back to the formal written solution of the problem, you can see that after I remove that area to the left of negative 1.5, then what I have left behind here is this area that's supposedly between the two z-score, the low and the high right there. Okay, and so finally concluding our answer, the way to get to our final answer, that area trapped between the two z-scores is simply just the bigger area, being 0.9798178, and that's a bigger area, came out from the area cumulatively to the left hand side of the upper z-score. And now I'm simply going to subtract out. Remember that demonstration where I removed out that area to the left of the lower z-score? And so now I'm going to take out, remove out, or subtract out 0.0668072. So usually when I meet with my student face to face, I tend to explain to them that we call this area from area to the left of the bigger z-score. I tend to call them it's a bigger area, and the lower z-score is going to produce, and of course we're only talking about the left area. So the left area, or the area to the left of the lower z-score, I normally regard to them as smaller area when I meet face to face with my students. And so the work here, simply just one step, we take a subtraction between, so bigger area minus small area, minus smaller area. And now our final answer comes out after calculation being, all right, so here we go, 0.913006. And once again, of course, every assignment that you are doing has a different rounding requirement, so I'm leaving almost complete precision here so that you can round to whatever you need to. And every problem in these days, either the WebAssign or My Math Lab or whatsoever, or YMath is looking for every problem is gonna have a different rounding requirements for that. Okay, and then you can think about this as an interpretation. It takes 91.3% of data being inside of that intervals of z-score from negative 1.5 to 2.05. Okay, so in the same example, let's look at a different problem. So this time, and once again, we are on the standard normal distribution bell curve. Having center at 0 and standard deviation sigma equals 1. And how about the question is asking, find the probability, and you have seen some experience in a very past problem right here. So take as much same experience as we can right here, but find the probability where our z-score is being anywhere greater than or equal to 0 and less than or equals to 1.5. And again, as usual, we are immediately after writing down the question, we are going to put the two z-score, the low and the high, on the axis. So 0 is here right in the middle of the bell curve, and 1.5 is somewhere to the right hand side. And so now we are going to make the shaded area. So cumulatively, this probability is how much probability or how much area we're looking to be inside of that interval from 0 to 1.5. And so here, allow me to give the detailed explanation again, even though you have seen that already in the previous problem, which is quite similar. But so in the understanding that every z-score from where it stands has an area cumulatively to the left, and that's what technologies can allow us to find. So from where 1.5 stands, and you can see that usually I start out with tackling down the bigger, the upper z-score of my interval, of our interval over here. And so from where the upper z-score stands, it's going to have an area cumulatively to the left-hand side. Okay, and the shading is right here. Okay, and of course it makes sense that we should make that shading go even way past that bottom end of our interval here. And so once again, calculations coming out from technology, calculation can quickly show, and you can use various different types of technologies for calculating this work right here, this amount right here. So on my area, on my LS&D program, 1.5 z-score gives me an area cumulatively 0.9331928. And so the area left, so the area left of positive 1.5 right here, we found that answer to be 0.9331928. And again, 0 is the lower z-score right here of our interval. So we think about, once again, the area to the left of 0, instead of making a shade, because you can see that again, the area we're looking for is not quite this big area. It's just the area being in between 0 and 1.5. And so as a planning right here, to get that area between it makes sense that we're now going to remove out the area to the left-hand side. Okay, and allow me to do that barbaric way, that barbaric solution of erasing out, but I intend to demonstrate the idea that we need to subtract out some area. Okay, and so that area I just now took out, that I just now removed out, is the area, that area there is the area to the left of 0. And to the left of 0, really, if you love using technology, then yes, here's you can use the LS&D program or many other programs. It should turn out exactly the same answer. And you can even do this without the technology. What is the answer expected to be? 0.5, because we already learned it. It's just halfway on the bottom end of our z curve right here. So that area to the left of 0 as a z-score, that area is 0.5. How's that? And so now we picked up these two terminologies from the very preceding problem, but this is what I regard as a bigger area, and this is what I refer to as the smaller area. And so the removing action that I was doing, taking out that smaller area from the bigger area, then what we have remained now is the amount of area exactly between, trapped inside of and between that interval from 0 to 1.5. All right, so back into the actual solution of our problem. Then the bigger area we're looking at now is being 0.9331928. And as I said, we call this area the bigger area. And now we are, according to that illustration that I did, that explanation that I gave, like that, and we're subtracting out, we're taking out, we're removing out the smaller area. So this is referred to as the smaller area. And the answer after final calculation comes out to be 0.4331928. And that is our final answer for this. And once again, be ready that in any assignment problem that you're going to have to be doing, and usually they ask for rounding to 4 decimals, then we can round this to a 0.4332 if we have to, or this is equivalent. This is the same as about 43.32% of data, different interpretation. All right, and so now as another generality that we can draw after the very previous two problems, then once again, anytime being on a standard normal distribution, and if we have the kind of problem where we're looking for area that is between two given z-scores, so z-scores are anywhere on this horizontal axis, and then of course 0 is right in the middle, and basically or generally we're having two z-scores given, and we are looking for the area generally being inside and between, inside that interval between A and B, or from A to B. Symbolically, the question is addressed as find a probability where z is anywhere greater than or equals A, or less than or equals B, or we can also skip the inequality. No change to the final answer, and the solution remains the same. So what we did throughout the problems we did in the examples is that we just simply need to find bigger area. And at this point, after a lot of explanation I gave as we were doing, then bigger area refer to the area to the left of the upper z-score. So bigger area comes out from that upper z-score. And then we're going to also need to find the smaller area, which is the area come out as the left area of the low z-score. So it's a little counterintuitive here that we should find a bigger area first, because it makes sense that way when subtraction happens. And then bigger area subtract smaller area. Okay? So bigger area subtract smaller area. And that provides our final answer for how much area being between two z-scores.